Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of this week, and today we will continue whatever the discussion we started in the last class. If you recall, we had taken some example. One example was this and another example was this, and we applied triangular element to get the solution. We had written a code, we browse through the code and then see different operations to be performed in finite element methods, and then when we applied that code to get the solution, first we validated the code and then we checked whether with increasing number of elements we get the solution we get from the finite element method, whether that converges to a value or not, and we have seen that is happening. Now today what we will do is we will do the similar exercise but with different elements. We will use quadrilateral elements today. As far as the implementation is concerned, the main difference is in quadrilateral element, we need to use the concept of isoparametric formulation. Okay. Now, so let us quickly revisit what is that. This is the equation, the general equation for elasticity problem in finite element, the element level equation. And then for quadrilateral element, now in this expression we need to compute this B matrix, which requires the derivative of the shape functions with respect to xy coordinate system, with respect to physical coordinate system. And in isoparametric formulation, the concept is the geometry and the field variables are approximated with the same shape function, and this is how the geometry is approximated. And then similarly this will give us how the derivatives are related, derivative with respect to the physical domain and the derivative with respect to the local coordinate system. So xi eta are the local coordinate system or natural coordinate system, and how these are related to the derivative with respect to xy coordinate system. And this is Jacobian, and Jacobian is obtained like this, and these are the shape functions for shape function in xi eta coordinate system. Okay. Now the idea here is simple. This B matrix, which is written in term with respect to xy coordinate system, that needs to be represented or written or expressed with respect to xi eta coordinate system using this transformation, and then the entire integration needs to be performed using numerically using Gauss quadrature rule. Okay. So let us go to the code. This is the physical domain. Once again, this is same. This is what are the divisions required in x and y direction. This is since here we need to perform integration using Gauss points. So these are the position, locate Gauss points and then corresponding weights. These are the properties. Now these are the body force and traction term, and then next is these are the identification of essential and natural boundaries. And then next is this. Next is, you see, our derivatives, these loop over, we have over I is equal to 1 GP and 1 GP, n GP, and j is equal to 1 to n GP. N GP is the total number of Gauss points or integration rule we have in any direction. Now phi 1, phi 2, these phi are the shape functions with respect to the natural coordinate system, and this is the derivative of phi with respect to natural coordinate system. In this expression, we need to compute the derivative of phi with respect to xy coordinate system. But now once we know the derivative of phi with respect to natural coordinate system, this can be mapped with the derivative of phi with respect to x coordinate system using this Jacobian. So derivative of x with respect to xy will be inverse of Jacobian into derivative of phi with respect to xi eta coordinate system. This equation, we have this equation, right? Now So once this is done, then rest of the procedure is same. We have now B matrix, then B matrix, then stiffness matrix will give you this. Stiffness matrix is not constant, so we have to evaluate the integration, evaluate this entire thing at every integration points and then multiply by their weights and then sum them to get the total stiffness matrix for the element. And the next is, this is the globalization is exactly same, only difference here will be, now here we have 4 nodes, in case of triangular elements we have 3 nodes, but the logic is exactly the same. Computation of body force term, the logic is exactly same in the sense here body force also need to be integrated using Gauss quadrature technique. In case of triangular element, we didn't have to integrate it, we could write the body force term straight away, but then here you have to integrate it. And then boundary traction term, this identification of the boundary of the element where the natural boundary conditions are prescribed. It is exactly same as the triangular element, and then once we have this, then rest of the code is exactly same. We identify impose the boundary condition, get the solution, and then after the plot it. Now, so next let us get the solution first. So first get just with one element, right? So this is with one element. Now let us write the this is the result with one element. Now let us see what was the results for triangular element. Triangular element, you see, this was the result for other problem, the elasticity problem. So you see, for triangular element, you recall we did not have, when we discretize with just 4 nodes, we did not have any symmetry in the solution, but here we have the symmetry in the solution, which is very obvious because our discretization is also symmetric. Now we can increase the number of element, say let's take 0.5, then this will be your discretization, and then okay, let's plot the discretization as well. This is the discretization, and finally you will be this. And if you recall, our converged result was something for triangular element, it was 11.16, and then one was 1.96 and almost 2 and minus 2, which is the same results we are getting, but with lesser number of element. Okay, if we further discretize it, and then if you check the result, this is almost, then last we will discretize with 0.125 and then check the result, and then see whether further change in the solution is happening or not, and we see that result is almost similar. So we can say that this is our converged result. Okay, now let's take the another example. If you recall, this was the example we also had taken, and then this was the elasticity solution, and this was the results we have for triangular element. And we have seen that in order to get the more or less very close to the elasticity solution, we had to use a discretization of this 0.0, this is 0.0625. Okay, let's see what happens in case of quadrilateral element. So let us start with first 1. Okay, let us start with 0.5 because that was the starting point for in case of triangular element for us. Okay, so okay, this was, let's take this for example. Let's take 0.5, this one, and this one is 2 into this. So this is the discretization, red is the deflected shape, and this is the plot of contour plot of probably ux. Let's see what is the results we have. Now multiply by 100. Let's see what is, this is the x1. It should be 2 into because we want to, this is 0.313. So let us write this. So this is minus 0.313. Let us take further discretize it, close it, make it 25. This is the discretization, and then 0.44. So this is 0.44 minus 0.44, and if you further discretize, let us further discretize it. It's 0.493. So this is minus 0.493. So whatever we obtained with 0.0625 discretization, we obtained. This was for T3. This is for Q4, or this is for LT3 linear triangle, 3-nodal linear triangle Q4. Now, so let us discretize. Now here you see our discretization was like this. In H direction, number of division is double the number of division in Y direction. Let us make it same and then check the result with 0.5. Yeah, this is minus 312. This is minus 0.312, and then 0.25. 0.441 minus 0.441, and then which is almost similar what we obtained, 125. 0.493. This is almost 0.493. Okay, now let us make a very fine mesh and then check the convergence. Let us make it 2 into this and make it 0.625. .508. This will minus 0.508. So one level of discretization is this same, minus 0.508. You see, which is very close to this solution. So even if you increase it, you can see the convergence. So again, the same observation from very coarse to this. Your rate of change in the solution is very steep, but as you move towards the converged solution, you will see your convergence is the rate. The convergence is this change of rate of change is very slow. So if you plot them, your plot will be something like this. Okay, and this will be your true solution. True solution almost. Okay, true solution. Okay, it will not be exactly true solution. It will not, theoretically it will not be equal to the true solution. Okay, but it will closer to the true solution. Okay, as we increase the number of elements. Now just to tell you general application, another problem. You see, for these two, all these problem our domain was simpler, so discretization was relatively simpler. But now next what we do is, we will take an example where the discretization is not that easy. Therefore, we have used a different software for the discretization and use that discretized data, the nodal positions and element connectivity for our solution, and it is stored in here. So this So this is the coordinates, this xy chord is the coordinates of the nodes, and then this gives you the element connectivity. This gives you, this gives you connect will give you the how the elements are connected. Then we can call this is the we can call this we can call this entire thing in our code, and then just okay, then run it. Okay, this problem is like this. If you have we have something, a domain like this, and in this domain we have a circular hole, and you apply some uniform traction here, and at this point you have, this was the domain. So naturally our expected deformed shape will be something like this, like something like this, and then so this will be our this is the deformed shape we have, and this is the plot of the primary variable, probably uy, it is plotted. Okay, so let us just only plot the deformed shape, then probably it will be clear. Let us not plot this, let us only plot the deformed shape. So this is the initial configuration, and this is the deformed shape. Now there are many sophisticated algorithm, then softwares available for discretizing a domain is a separate branch altogether. That there are, it's not that easy job. I mean, for a triangular domain it is fine, but then the algorithms are the separate branch altogether. So once you have that discretized data, you have a domain and discretized with different kinds of element, then you have all the information of that discretization, and that information you can put in your code to get the solution. Okay. Now, so with this, let us stop today and also conclude this week. So this code will be okay. One thing we have not done in the class, that is computation of stresses. Computation of stress requires derivative of the shape function, and the kind of shape function we have used here, there the global continuity is C0, means the function is continuous but the derivative is not continuous. So naturally at the inter-element boundary these derivatives are not continuous, and therefore the stress, when you compute with this derivative, the stresses will not be continuous at the inter-element boundary. Okay. Therefore, when you calculate stress is generally computed as the Gauss points. Okay, at the element level. You recall in one of the weeks when we discussed how to compute the implementation part for scalar field problem, we had to compute the flux term, and there also we computed the flux term at the Gauss points. Similarly, stress at the Gauss points will be exact. And then one thing you can do, you can project what of the Gauss points, the values you have from stress value you have at the Gauss point, you can project to the nodal point. But then at the node, which is a common between various, for instance, if you have a connection like this. If you have a connection like this, so this is one element, this is another one element, this is 4 element, and you have a common node. So you calculate the stresses at the Gauss points, all these Gauss points for individual element. But suppose I want to see what is the stress at this point. So then you can you can project at this point. You will be having contribution from this element, this element, this element, and this element, and when you project that, you will see that the contribution of these elements are different, which is obvious because you will be, these derivatives will not be continuous at this point, at this junction, right, at the inter-element boundaries and at this junction. So one way you can get the stress at the nodal point is whatever values you have obtained from different elements and then average it. But that will give you an average stress at the nodal point. Therefore, the Gauss point, the stresses at the computed at the Gauss point is exact in the sense which you obtain directly from the equation. Now, but that exercise we have not done in the class. I leave it to you. This course will be uploaded on the forum. If you have any difficulty, you can post your query on the forum, then we will see. So with this, let us conclude this week. See you in the next week. Thank you.